So it's our great pleasure to introduce today our almost last, right, but not quite last speaker of the seminar. Give me a sec. So Debankur Mukherjee from the H. Milton Stewart School of Industrial and Systems Engineering at Georgia Tech is speaking with us today, and he got his bachelor's degree in statistics from the University of Calcutta in 2012, and he has a master's in statistics from the Indian Statistical Institute from 2014, and his PhD in stochastic operations research with cum laude distinction from Eindhoven University in the Netherlands in 2018. So he is here today to talk to us about the coupling approach to mean field analysis of structurally constrained large-scale systems. And just as a reminder to everybody here today, Debankur, if you can make a quick little stop somewhere in the middle to allow for questions, would be much appreciated. If you want to say anything, feel free to write questions in the chat and we'll try to make sure that they get heard. And other than that, please take it away. Welcome.
Thank you, Mariana, for the introduction, and thanks to all the organizers for inviting me. Like, it feels wonderful to be here as a speaker after hosting so many talks till last semester. So yeah, today I'm going to talk about some recent advances on the mean field analysis of structurally constrained large-scale systems. Most of the talk will be joint work with my PhD student, Dan Rutten. So he might be in the audience. I don't know if he's already in the audience or not. In any case, feel free to ask questions in the chat box, stop me at any time for clarification questions. And I'll of course give some pauses, brief pauses for longer questions. Okay, so I'll start with the gentle introduction to the setup, but with so many talks on load balancing in the same seminar series and Christie's nice talk only 2 weeks back, I don't think I need to spend much time introducing the setup to this audience. A canonical model for load balancing consists of a bunch of servers. Here N is 10, N servers, and there is a dispatcher. There can be multiple dispatchers. Each server has its own queue and it serves its own queue. Whenever a task arrives from the outside world to the dispatcher, it needs to be assigned to one of the queues instantaneously, where it waits until served. For historical reasons, this is called the supermarket model. And in fact, one of the reviewers in one of my papers recently mentioned that this term actually may have come from Frank Kelly's team at Statistical Laboratory at University of Cambridge. Okay, and throughout the talk, I will be focusing on homogeneous systems. That is, servers will have identical processing speeds. And my motivation is large-scale systems, data centers, cloud networks. So I'll be focusing on large N asymptotic regime. There are many load balancing policies, various trade-offs, and it has been extensively studied field. I'll focus on JSQD, or the popular power of D choices policy, where each arrival selects D fixed number D servers at random and joins the shortest queue among the selected servers. Now, starting from the work of Midzenmacher and Vedenskaya, Dobrushin, Karpelevich, it has been a huge success in understanding these performance of these systems via classical mean field approach developed by Kurz, Norman, and so on. However, in many modern systems, we see that the individual queues often interact among themselves in a very non-trivial way. For example, and that leads to somewhat what I call structurally constrained systems. So one constant that I will focus on in this talk is due to task server compatibility. In fact, what happens is executing a task of a particular type requires some pre-stored data, like some specific type of servers and so on, specialized servers. And it is often infeasible to design a fully flexible system where any task can be served by any server. So that is too much. It will lead to overwhelming implementation cost, and due to data locality, it will lead to an enormous storage capacity requirements at the servers to load all those resource files for all different task types. So an arriving task is often constrained to be assigned to some prefixed collection of small number of compatible servers. So certain exchangeability assumption that we assume in classical mean-field analysis, that is lost, and that creates a lot of issues that I'll come discuss in this talk. Of course, there can be other types of constraints. Constraints can come from various sources, as one can imagine. It can be geographical constraints or spatial constraints. Some of these have been discussed in these papers as well. Now, in summary, what it means is that we need to design and analyze systems with sparse interaction structure, where such dense interaction of full flexibility is not there. So that is the summary of this, the main takeaway. And in this case, once there are constraints, the mean field approximation becomes highly inaccurate. So here I just like to point out that this dotted line here is the mean field limit, and the green line is, I guess, for n equals 1000, like finite n system, the performance of that for fully flexible system. And they are nearly indistinguishable even for n equals 1000, 2000, and so on. But as we go to some compatibility constraints, even if it is not so sparse, if it is very sparse and separate, but even if it's not so sparse, the performance can differ really arbitrarily from the mean field approximation, what we would expect via this mean field analysis. However, and the main thing is these systems are arbitrary, but just to the takeaway is that the difference, the approximation accuracy can be really bad. Like there can be no connection between the two. And I'll discuss some concrete examples, this effect via some concrete examples. However, if we design the compatibility constraints or the constraints carefully in the context of data locality and compatibility constraints, by placing the resource files appropriately, if we design such a network with the same level of sparsity, one may be able to retain the performance benefits of a fully flexible system, and can have this, again, the mean field approximation will remain valid. So an overarching goal for us is to extend the validity of mean field approximation to sparse interaction structures. In particular, what we ask is, what is the sparsest interaction structure that can retain the validity of mean field approximation or has the same asymptotic performance as the fully flexible systems? To be more precise, we are interested in macroscopic system description or macroscopic performance. That is, this Qi is the number of servers with queue length at least I at time t. And this small letters will denote the corresponding fluid scaled quantity or the proportion of servers with queue length I or so. And we want these quantities to behave similarly or to have the same asymptotics as the fully flexible system. Now, there is one robustness viewpoint as well that one can note is like we want to formulate the result involving the robustness of empirical queue length process in the space of graphs. So we want to say something like, if the constraint structure belongs to a certain broad class of graphs that contain the fully flexible system and a lot of sparse networks, then that much is enough. We don't need to check anything else. The behavior will be same as the fully flexible system. That viewpoint one can look at as well. Okay, so yeah, so now let me be concrete and introduce the model that I'll be talking about. So Vn will denote the set of servers. Okay, so these are the this is Vn, and the number of servers is n for the n system, And these are the set of dispatchers or task types. So throughout, I will be using the terms dispatcher and task types interchangeably, because like one dispatcher can handle one dedicated stream of arrivals and so on. So these are the dispatchers. And there is a bipartite graph between this Wn and Vn, which is denoted by Gn, which is the compatibility graph. That means task type 1 in this picture can be served by server 1, 2, and 4, and so naturally how one would model. And all the interarrival times and service times are exponentially distributed, and the mean service time is 1 without loss of generality. And we assume homogeneity in terms of the arrival rates as well. And the arrival rate is lambda n over mn, since this mn is the number of task types. So the total arrival rate is lambda times n. And for ergodicity, we'll assume lambda to be less than 1 throughout the talk as well. And we'll focus on the asymptotic regime as both n and mn tend to infinity. We do not restrict any relative growth rate of n versus mn. We allow everything. Okay. Now, with this model, note that the degree of a server in Gn is essentially saying that how many different task types it can serve. For example, server 2 can serve task types 1 and 2 and so on. So this degree of a server is roughly proportional to its storage capacity requirements. So whatever notion of sparsity we'll discuss or we will be coming up with, that should focus on reducing the server degrees suitably. Okay, so that is one sparsity. Okay, and the task assignment scheme is JSQD or power of D policy, where each arrival now selects D compatible servers. That means these are the task types again. So suppose a task of type 3 arrives, and here suppose D is 2, then it selects 2 random neighbors in that graph, 2 random compatible servers, and the task joins, and the task joins the shortest queue among those 2 selected compatible servers. Okay. Now, what is so hard about these models? Even with all the homogeneity assumption, even even with homogeneity assumptions, the graph structure, the compatibility, the restriction or the constraints pose significant challenge. And what is that? One, like I'll note a few that can be fit into one slide. There are many other intricate challenges as well, but from a high level perspective, one issue is that the system performance is non-monotone with respect to age addition. That means it's not always true that introducing more flexibility will lead to a better performance. In fact, ill-designed compatibility graph can even turn a stable system unstable when additional ages are added. Again, even for the homogeneous system. Let me start with one toy example. So suppose each dispatcher uses JSQ2 policy. Okay, so suppose we have, to begin with, we have this simple system, almost trivial system, independent servers. So task type 1 can be served by server 1, task type 2 can be served by server 2, that's all. It's like independent system. All lambda, all 1 departures and arrival rates and departures. Now, okay, now we feel generous and we add a lot of ages to it. And we say that we equip this task type servers 1 and 2 with more resource files, and we say that, oh, now these 2 servers are able to serve all task types. So in this case, observe that what will happen is like the server 1 and 2, if task type 1 and 2 arrives in the system, they must be routed to servers 1 and 2. They don't have any other choice. At the same time, if a task arrives at, say, server 6, with some probability, they will select these 2 red edges. And those tasks will have no other way but to be assigned to servers 1 and 2. And consequently, the load at servers 1 and 2 will be much more than they can handle, and they will be congested here. So this structure of this compatibility structure is really affecting the performance even at the ergodicity or stability level, and finer influences, of course, there. Okay. So this is, of course, a pathological example. The point of this toy example is to demonstrate that the performance can depend very non-trivially on the compatibility structure. That's the takeaway. Another point is, another difficult to handle aspect is that queues are non-exchangeable. Like each queue looks at different parts of the system and all of them are non-exchangeable, and the queue length vector is non-Markovian. So if we are given all the queue lengths, then also the system is not Markovian. And as a result, something is happening. Yes, okay. And as a result, there is no tractable Markovian mean field quantity that one can view as an aggregate. And this is perhaps the most crucial challenge that we need to handle. That in all the mean field analysis, what we have done is, in the past, that we look at, say, proportion of servers or fraction of servers with queue length 2, say. That is a function of a lot of weakly dependent processes, and that is Markovian under the exponential assumptions and so on. So that sort of averages out, and they start to behave deterministically. But here, this number of servers with queue length 2, 3, so on, such mean field quantities are not Markovian. So there is no a straightforward way to analyze these type of macroscopic behavior. Okay, so that is another issue.
Question?
Yes, sure.
When you say they're not Markovian, you mean that they're not Markovian with a really reduced state space, right?
Yes. Yes. So by Markovian, I mean, okay, the queue lengths, if we keep track of all the individual queue lengths along with their identity, along with the graph structure, how they interact, then they become Markovian. But that is a huge state space to work as a mean field limit. And if in traditional mean field limit, we reduce that huge state space into some aggregates. And that is problematic here. That can be done. Yeah. Any other question?
I had one more question about this edge addition. So the way I think, so I sort of missed this. So when you define these M of N categories, the way I thought of it was that each category has all the D edges. So there is no more randomization. Once I pick my category or class, I pick shortest of all the outgoing queues. In that here you're just adding more categories. So this sort of the thing that's arriving to 6 and it picks 1 and 2, it's like one more category. And in some sense, you're saying adding categories creates instability and not adding edges. I mean, sort of, I don't know if I sort of.
So here, for example, the number of categories are fixed. So there are 6, for example, task types and 6 servers. So initially we looked at the first system where it's this independent. Now we load these servers with more resource files so that now they can serve all the categories or all the task types. And then they start behaving like the system starts to become starts to behave very weirdly, and it becomes unstable. But if you are looking at all the queues, then the scenario is very different. So one thing I'd like to, this reminds me of one point, is that this instability is not the property of the graph itself, it's the property of the compatibility structure along with this JSQ2 policy. So these two in combination, that is not a good combination, and that makes the system unstable. Yeah. Okay. All right. So what we do is we look at arbitrary deterministic sequence of graphs with certain expansion properties, and we do not need any vertex transitivity or assumption on starting state. Now, these two I have put because in literature, these two played a crucial role in characterizing certain limits and so on, but we don't need any such assumption. We characterize both process level limit and the convergence of steady state. Now, this process level limit, as I will mention, that becomes important if the load is time varying, for example, and we are able to handle that as well. Those who are familiar with the literature of random processes on random environment, we prove quenched limit loss when the underlying compatibility structure is random. And we'll conclude that much sparser compatibility structure can indeed enjoy the performance benefits of a fully flexible system that is a complete bipartite graph. Okay, so our high-level approach is we'll show the convergence results, all the asymptotics for deterministic sequence of graphs, fixed sequence of graphs having certain properties. And then we'll show that those properties are satisfied almost surely if the graph is suitably random. And that's the quenched results. And for the rest of the talk, we'll mainly focus on the deterministic sequence results because they contain most of the ideas. And the random graph results essentially follows by standard concentration of measured arguments. Okay, so I'll start by mentioning one related model that has been analyzed in the literature, is where the servers are interconnected by some graph topology, not really compatibility structure or bipartite connection, anything like that. Rather, servers themselves are connected by a graph topology GN. There is no dispatcher in this model. Each queue faces an stream of arrivals. And whenever an external arrival occurs at a queue, say here, then it selects a fixed number d-1 neighbors. So here it has neighbors this, and these queues. It selects, say d is 3, then it selects 2 random neighbors, and it joins the shortest queue among those 2 selected neighbors and where it appears. Okay, again, for this model, if the graph is fully connected, then it behaves like classical join the shortest queue, JSQD. And I'd like to mention that this model cannot really be used as this task server compatibility or not that level of generality. However, if these edges were directed, then that directed version of the model can in principle be viewed as a special case of the model that we are considering, where Mn and N, the number of task types and servers, they are equal, and when there is a perfect matching, like dedicated stream of arrivals per server. That special case can in principle be viewed like this So in this model with Amarjit Budiraja and Ruoyu Wu, we showed that under certain conditions on the graph structure, if the initial queue lengths are IID, all the queue lengths, then the asymptotic independence holds on any finite time interval. That means we show that if the queue sort of starts with an IID state, IID queue lengths, then if we look at as the system size grows large, if we look at any finite time interval, then any collection of any finite number of queues, they remain independent. They sort of maintain their independence throughout the finite time interval. And we use some asymptotic coupling with infinite dimensional Mac-Vlasov processes to establish that. But here, the structure of the model, that means this Mn equals N, and the fact that the initial queue lengths are IID, so they are independent to begin with, or at least exchangeable to begin with, that fact has been used quite crucially to show this convergence. And that's why these techniques cannot really be used at the level of generality that we are seeking, that arbitrary growth rates of Mn and then time varying with process level and steady state. Among other related works, I'd like to mention a few. So there are some preliminary models that focus on such routing, some tasks having no routing options and some tasks are flexible as well. So these line of works, they consider more general model than what we'll be talking today, but their focus is on stability properties for fixed N and looking at traditional heavy traffic limits and so on. This work by John Cisiklis and Kuang Shu, that is very relevant to ours. They look at large-scale systems as well, but they look at input queued processes or input queued systems and scheduling side of things. And their goal is not to characterize the performance of the system, the limits, steady state, not like that, but they are interested in having large capacity region in terms of the constant factor of the maximum possible. So with Sam Borst and Johan van Leeuwarden, I had looked at earlier this non-bipartite model that I explained in the previous slide, and JSQ on top of that. There, one advantage is that this non-monotonicity that I mentioned is not there. Adding edges is always beneficial. It's always better. And there, the insight is very different in the sense that it depends on being able to identify the almost shortest queue. So if my neighborhood size is really large, then the hope is that I'll be able to, like, almost all incoming tasks will be able to identify almost shortest queues, and that can help us to make the system sparse. And this recent work by Wang Zhu and Shrikant, they look at the same model as I'll be talking today, this bipartite model, but they look at heterogeneous server speeds, they provide finite end bounds, and they look at join the idle queue type policies, not the JSQD type policies. And their insight also somehow somewhat depends on being able to find idle servers as well. Finally, yeah, sorry. Yeah. So finally, I'd like to mention a broader context of stochastic processes on large graphs. This is a huge area, and the work fits there as well. This list is highly non-exhaustive. There are a lot of works. I have just selected few few works, just to few representative works, so that the interested those who are interested in the audience, they can look at these and the references therein. It fits there in the interacting particle systems on graph literature as well. Finally, there's another line of interesting work by Vijay Subramaniam and his student. They also look at processes on graphs, but their motivation is very different. They look at random walk-based sampling to reduce the amount of randomness used to implement JSQD policies in a network. Okay. All right, so now let's move to our model and results. So brief state description. Xi will denote the number of servers with queue length I, and all the small letters will denote the corresponding proportions, the fraction of servers with queue length I. And so NW will denote the set of neighbors of W in Gn. So those are the set, like the set of compatible servers for a particular task types. And XIW will denote the number of queues of length I that are neighbors of them. So this is the global quantity. This is sort of the local quantity, which are the neighbors of a particular task type. And the small XIW will denote the proportion of neighbors with queue length I. Just note that this is not N, this is NW, so proportion of the neighbors that are queue length I. So throughout the talk and analysis, I will sort of keep referring to two quantities. One is a local quantity, one is a global quantity. So this x1, x2, so on this vector, I'll call it global empirical queue length distribution, or GEQD, and the small letters, I mean this quantity is corresponding to each W, each task type. I'll call it local empirical queue length distribution, or LEQD, for each task type W. And of course, our quantity of interest is the global quantity. That means number of servers with queue length at least I, at least 1, at least 2, at least 3, and so on. This global quantity and the corresponding proportion. And here I'd like to point out that this quantity, this process is non-Markovian just by itself. So we need to work with these descriptions somehow. Although these are also non-Markovian if we are given just that information. Okay. let's go to. Okay, so we'll follow the limit interchange argument, and we'll start with the transient limit or process level limit as n tends to infinity on any finite time interval. So to state the result, we'll introduce one notion of sparsity, which we call proportional sparsity. Recall these quantities from the last slide. Now, so the notion of proportional sparsity is as follows. A sequence of graph, bipartite graph, is called proportionally sparse if the following condition holds for each epsilon positive. Let's see, let's understand what this quantity is. So fix any subset of servers, U, okay, U subset of Vn, fix any U, then this is the difference of two ratios. The first one is saying what for any W, what is the proportion of neighbors of W that are inside U. So this is this quantity, and this is the ratios of proportional neighbors inside U. And this quantity is saying what is the size of U. Okay. And this one is saying that for W, this event or this this event is saying these two numbers differ by more than epsilon. And what proportional sparsity is asking is supremum over any U is mainly the large U's are here that are important. Supremum over all U's for which the number of supremum over all U's, the number of W's for which these two numbers differ by more than epsilon, that should be small o mn for any positive epsilon. Okay. Now let's understand this in a bit from one different angle. So for once, let's pretend that this quantity is exactly zero. So it's not going like after being scaled with mn, it is going to zero. Forget about that. It is exactly zero. Let's imagine. And let's also imagine that this quantity, this ratio is same as this quantity for all U. This is also equality. There is no epsilon. In that case, there is a unique solution in the graph space that satisfies that. That is complete bipartite. Okay. So now we are allowing two sparsification or two types of sloppiness or sparsification that we are allowing here. First, we are saying, well, these two quantities do not need to be exactly the same, but it's okay if they are at most epsilon away of each other. It's fine. That is one level of sparsification. And then we are saying, well, we do not need this for all W's as well. It is okay if there are some W's that do not satisfy this assumption as well. But that number of W's should not be too much. There should not be too many such W's. So this is the second level of sparsification, which is saying relative to the number of mn is, remember that mn is the number of dispatchers. So relative to the number of the cardinality of V, this number should be small. Suddenly, we'll see that from that unique solution, there are many graphs, especially many sparse graphs. In fact, exponentially is many sparse graphs. When we go to the random graphs case, there are many graphs, many sparse graphs that actually do satisfy this this condition asymptotically. Okay, and this condition is somewhat related to the well-known condition of quasi-randomness developed by Chung, Graham, and Wilson. But ours is a little bit more general in the sense that quasi-randomness implies proportional sparsity, but not the other way around. And the reason that the converse is not true is we can allow certain inhomogeneity on the side of dispatches, on the W side as well, whereas quasi-randomness doesn't allow that. So that is the reason the converse is not true. Otherwise, they are quite related. Any question about the notion of proportional sparsity?
I have a question. So I'm just confused about the word sparse, because like you said, if I relax these epsilons and the little o stuff, what you get is the densest possible graph. Then why are you calling it proportional sparse and not proportional dense?
No, okay. So what I wanted to say is, if these relaxations are not allowed, then we get this highly dense graph that is complete bipartite. Now, as soon as we allow two types of relaxations, that, well, some wiggle room, say, then a lot of sparse graphs are there that actually satisfy this condition.
Okay. Yeah, kind of. I mean, like, for example, I can say a complete bipartite graph is proportionally sparse, right? That's a correct statement.
Yes. Oh, I mean, the class is not like that. Class is proportionally sparse, meaning what I wanted to mean is that it contains a lot of sparse graphs.
I see.
Yes. I mean, a graph satisfying this condition, you're right, that doesn't necessarily mean that it is sparse, that I agree, but it contains proportional, like sparse graphs as well. Yeah.
Okay, got it. Thanks.
I have a question about this parameter epsilon. So this is the parameter you chose, and so then your graph satisfy epsilon proportion sparsity, or it's for any epsilon that is greater than 0?
Yes, that's a very good question. So so we need, in order to have the exact same fluid limit, I'd say, or same mean-field limit, we need this to be to hold for any positive epsilon asymptotically, like first fix epsilon, then take n tends to infinity limit. That should be that should go to 0 for any fixed epsilon. However, this notion can be relaxed. Like if we are not interested, or if we do not need the mean field limit to be exactly same, rather it's okay if the mean field limit is a little bit close in suitable sense, then having a threshold of epsilon may make sense. All right, so that was the condition on the graph sequence. And now, although I started by saying that we'll be looking at JSQD policies, but actually we can consider a bigger class of assignment policies. So we identify the assignment policy, one assignment policy pi, by what we call assignment probability function. So a policy pi is identified with the function p pi. Say this is a function that takes input the local empirical Q-length distribution, and then it gives us what is the probability that an incoming task will be assigned to a Q of length I. So if we are given this local empirical Q-length distribution at W, then this function will be able to tell us probability that when the local empirical Q-length distribution is XW, what is the probability it is assigned to a Q-length 1, 2, 3, 4, and so on. Essentially, this is saying that the policy does not distinguish two servers with same Q-length. So it's a Q-length based policy. And what we need is this assignment probability function to satisfy some Lipschitz continuity property, and we call a policy to be K Lipschitz for a fixed number K if this Lipschitz condition holds, if the P function is Lipschitz with respect to L1 norm. So now, for example, JSQD policy belongs to this class, and that is Lipschitz continuous with respect to, with constant is some 2D factorial times G square and so on. Okay, but not all the policies satisfy this condition. One example of the policy that does not satisfy this is JSQN, or the classical JSQ policy, because you'll see that if the my local empirical Q-length distribution, in the local empirical Q-length distribution, the minimum Q-length is 4, say, then this P function will have probability 1. With probability 1, it will assign to a Q of length 4. Now, if there is a single departure, then the probability function will change to another vector, which will assign the task to Q length 3 with probability 1. So this is very sensitive to the empirical Q length distribution. So what this assumption is essentially ensuring is that my assignment decisions are not too sensitive to the to my neighbor, the probability distribution, to the Q-length distribution in my neighborhood. Okay. Now we are ready to state the transient limit or process level limit. Recall that this is the fraction of servers with Q-length at least I. So what we show is that if Gn is a proportionally sparse sequence of graphs and pi is a K-Lipschitz continuous policy with assignment probability function this P, then these vectors, like this process, converges weakly to a limit given by the unique solution of the following system of ODE. Now, exact description of ODE is not important here. What is important is this is same as the fully flexible model. Okay, so that means the on any finite time interval, we see the same asymptotic behavior as the fully flexible system. Here, I would like to again point out that this convergence we are getting, but this is not a Markovian process, but still we can define the underlying Markov process and view this quantity as a functional of that Markov process. And still we can define the limit, everything, there's no issue. And we can say that this is the limit of that process. And as I initially mentioned, that this transient limit holds for if this lambda is lambda of t, essentially, like if it is time varying as well. Okay. So now let's move on to some proof ideas, and there are some ideas that I wanted to share. Is the proof of this process level convergence works at multiple steps, and different coupling arguments are involved. The first step is proximity lemma, what we call a proximity lemma, which says that these LEQDs and GEQDs are close in suitable sense, somewhat uniformly. So what it says is that if Gn is a proportionally sparse graph sequence, then LEQDs are uniformly close in L1 to GEQDs for almost all vertices. That is like the following event, that means uniformly over any finite time interval, the number of W's at time t such that this difference, L1 difference, is more than epsilon, that is small with respect to the total number of task types of dispatchers, that goes to 0 in probability. Okay, now the idea of this proof is very simple, and so that it's like almost 3 lines, so I will be able to sketch the proof idea here. So first observe that for any fixed Q length I and any time t, fix those two. And then look at the following bad event. The bad event is saying that the number of dispatchers, number of task types for which the proportion of queues in the neighborhood differs from the global quantity, the global proportion of queues with Q length I. These two quantities differ by more than epsilon. And number of W's that bad event happens is more than, say, delta times mn for some small delta. So this is our bad event. Okay. Now, using simple Markov inequality, we can upper bound this quantity by the corresponding expectation divided by delta times mn. Fine. Now let's look at this event itself. This event is very spatial event. Why? Because this quantity we can define, think about it like this. At any fixed time, there is a specific set. We can define that the set of servers with Q length I, that is a global set, well-defined set. This is saying the size of that set, the global size of that set. And this one is the proportion of my neighbors that belong to that set. So you may have guessed it that this quantity can be written as this proportion. So U is the set of servers with Q length I. Then this quantity gives us the proportion of my neighbors within that set. And this is sort of the relative size of that set. And this event is saying that they should not differ by more than epsilon. And since we have the proportional sparsity, this quantity, of course, goes to 0. That is the simple idea. And of course, this needs to be extended to the L1 distance, and we need to achieve some sort of uniformity over time and so on. But those are only technical. That makes the proof long, but the key idea lies there. Okay. Any question so far? Just let's pause for a moment.
I have a question about the proportionally sparse assumption, because that plays an important role here. So Jing pointed out that what you need is for every epsilon, you need this, right? And then if I have fixed n and then I make epsilon equal to 0, then it's kind of like the complete bipartite graphs. So essentially the definition is saying that in the limit, it's behaving like a complete bipartite graph. So my question is, are there examples of sequence of graphs where in the limit, it's not complete, whatever that means, but the assumption is satisfied?
Yes, there are. That's the, in fact, thanks for the question. That's the main punchline. Like there can be way sparse graphs, and I will come to that when we go to the random instance. But there are many graphs that actually asymptotically satisfy that condition, but they are far from being complete.
I see. Okay. Cool. Thanks.
Any other question?
Actually, I have one more question in the main theorem.
Yeah.
You said that the ODEs are like that of JSQD. What are p-pies in that case? Here? The ODE you said is like JSQD. So for JSQD, what is p-pi going to be?
It's like, I guess it's Q, the probability that it will be assigned to Q length I is the probability that it will, like no Q of length I minus 1 will be selected. And everything else will be selected, or at least one Q of length I will be selected. So it's like Qi to the D minus Qi plus 1 to the D, and this in this form, like there will be I minus 1 probably, or Qi to the D minus Qi minus 1 to the D, or something like that. Yeah.
I see. So you're saying the ODE is like this p-pi I you have for a particular policy need not be the same p-pi that you see in JSQD, right? So you're saying the ODE is like in JSQD, you remove whatever the probability is and put this p-pi, that's the ODE you get.
Exactly. Exactly. In fact, like this ODE, like if you have general p-pi, then the corresponding ODE can be proved, like it doesn't have to be JSQD, but other, it can be some other policy, but you'll get this ODE essentially as in the process level limit.
Okay, got it. Thanks.
Okay, now, so that was the first step, the proximity lemma of the LEQD and GEQDs are closed in an uniform sense. Okay, now the next step is what we call optimal coupling. So this is the coupling between two systems now, GN and the complete bipartite graph, which is K and M. Okay. Now, for this coupling, the departures are is easy. So synchronize the departure epochs of kth ordered servers, like order the servers according to the queue lengths in both systems, and synchronize the departure epochs of the kth servers. Since we can do that since everything is exponential. Now, coupling arrivals is the most tricky part. So there are two different graphs. One is GN, one is complete bipartite, but they have same number of task types and so on. So we can synchronize the arrival epochs at different task types. Now, suppose a task arrives at dispatcher W, and let's assume that XW is the local empirical queue length distribution for GN, and YNW is the local empirical queue length distribution for the other system, the fully flexible system. What we'll do is optimally couple them of these two, the routing decisions. Now, here is one subtle point in defining going to the coupling approach in the when the graph starts, like the constants is non-trivial. The main problem with that is, observe that even if the number of task types and number of servers are the same, each task type has different neighborhood structure in the two systems. So in one system, it can possibly be routed to a small number of task servers, and in other systems, there are many possibilities. So we cannot hope to couple the exact routing decisions, because they will of course be routed to two different servers. So the individual server queue lengths cannot be coupled. So we need to come up with some local this LEQD, GEQD based coupling somehow that we'll demonstrate in the next slide. That is one subtlety that is very important here. Okay, so the optimal coupling, recall that x omega is the xw is the LEQD for GN, YW is the LEQD for complete bipartite, and these are the corresponding probability vectors. So how this coupling works is essentially how one would couple two countable support distributions in an optimal way so that their total variation distance is sort of small. So define this PI is to be the minimum of these two quantities. So the red bars are sort of the for GN, and say the green ones are for KNM and so on. And P1 is the minimum of these two for different i's. Okay. Now we draw a single uniform random variable, and in GN, a task will be routed to some server with queue length I if this uniform random variable belongs to the union of two different intervals, where the first interval is saying that take all the partial sums of this minimum quantity up until I minus 1, and it is between and up to the partial sum up until I. So the length of this interval is essentially Pi. Union, take the entire sum of these minimum quantities up to 0 to infinity, and now observe that these individual bars can be different. Like it can be like, for example, this green bar has an extra. This is extra probability. So add those extra probabilities, and whenever it crosses the ith threshold or ith partial sum, include that length as well. So marginally, the probabilities do not differ from this Pi x omega xw and Pi yw. Okay, so that is how we take decision in GN. And then for KNM, if we replace everything, all the x's by y's, then the same with the same uniform random variable, we can take the routing decision in KNM as well. Now, once the server, once the queue length is selected, then we can route it uniformly among the queue length. So it doesn't really matter where do we actually route it. Okay. Now, with this optimal coupling, it is not hard to verify that it sort of minimizes the probability that the two realizations of the random variables will be different. That means probability that the task is assigned to two different queue lengths in the two systems can be upper bounded by this L1 sum. And now, using our K-Lipschitz assumption, these are upper bounded by the difference, the L1 distance of the LEQDs of the two systems at that moment. Okay, so this is one observation. Now to summarize, so what we have seen is the LEQD for GN, the local empirical queue length distribution for GN, and the GQD for GN, they are close. Okay, that is the proximity lemma. In the next step, what we see here in this statement is if the LEQD for GN, this is the LEQD for GN and GN and XN. So if the LEQD for GN is close to LEQD for KNM, if there is an if, then the routing decisions are also close. That is the optimal coupling. So, and also finally, we know that LEQD for KNM is same as GQD for GNM because the local and global are the same. It is fully flexible. So there is no local actually. So with combining 1, 2, and 3, we hope that the GQD for GN will be close to GQD for KNM. That is, it should imply that. And we'll see that indeed that is the case. What we show is this proximity lemma, optimal coupling, and Lipschitz continuity of task assignment policy implies that for any epsilon positive, the L1 distance of, at any time point, the L1 distance of the GQD of GN. Now we have moved from local things to global things. So these are both global quantities. The global quantities, the L1 distance of that can be stochastically upper bounded by something like this, but the exact description is not important, but Z is a rate 1% processes. So with this and some Grunwald's inequality type argument, we can show that the GQD for GN and the GQD for KNM have the same weak limit. Okay. Any question so far about the optimal coupling or proximity lemma, things like that?
I'm a little lost. In the previous slide, in your 1, 2, 3, you had a if, right? So what happened to that if?
That if is hidden in the proof, basically. That is non-trivial, but it is it is a somewhat of a circular kind of argument where this Grunwald inequality type argument takes care of that. Like none of them can escape essentially, so that needs to be tackled a bit carefully. Yes.
Okay. Cool.
Okay, so now that completes the proof of transient limit. So how much time do I have? Okay, so in 4 minutes. Okay, so in 4 minutes, all the 3 steps. So hopefully I'll be able to cover all of them. But anyway, so let me just quickly go through the stability. Oops. Yeah. So for stability, it's also non-trivial, and we needed to develop a condition called the subcriticality condition on the sequence of graphs that will ensure stability. But this is not new. Bramson in his 2011 paper considered a much more general system, which from which we get this as a sort of like a corollary. So there is not much that is needed. It essentially is saying that if there is a static randomized routing policy that can stabilize the system, then the corresponding JSQ version is also stable. This is essentially saying that. But what is highly challenging here is the tightness. In this paper and in general, showing the tightness for such a complicated system, even if the system is ergodic, that is the main challenge. And in particular, we need to show a particular type of tightness in what we call L1 omega topology, which is a weighted L1 distance, where distance between x and y is this weighted sum of the individual distances for 2 vectors. So what we show is that Gn satisfy if Gn satisfies subcriticality condition, then for any positive omega that has this following structure, that omega is sort of geometrically growing after a certain coordinate. And here, crucially, note that this R is more than 1. We are not diminishing the tail influence of the tail, rather it is growing geometrically. In that case, these random variables, again, non-Markovian, but as a functional of the Markov process, these random variables is tight with respect to this L1 omega topology. Okay. Now, why we need L1 omega topology, I'll briefly mention, I hope to mention it very briefly. But let me mention the proof of tightness. So we need a very strong and uniform control on the tail of the Q-length process, the global Q-length process, for which we look at a sequence of Lyapunov functions, V and K. So this is double sum. Observe that this is already a sum because it's number of servers with Q-length at least I. Then we take this, consider this double sum, and we bound the drift, appropriate bounds for the drift of this Lyapunov function. And then what we show is that the expectation of this partial sum satisfies a certain recursion equation. Okay, now here one thing plays a very crucial role. So this recursion we get from this Lyapunov function and these quantities. But then we need to show tightness. How do we show tightness? For that, we use a certain form of optimization type of technique. What we show that consider all deterministic sequences, the set of all deterministic sequences that actually satisfy this recursion. These are sequences, right? Now look at the worst case sequence in that class of sequences satisfying this criteria. For that, we show that such a statement holds. So we use that in the proof of this lemma, this tightness. Okay. So that is, and in view of time, I will just move on. And then why do we need this L1 omega topology? That is for the global stability result. Actually, what we need to show is that the limiting dynamics actually converges to the fixed point as t tends to infinity. Okay. So for that, what we show is that we consider this potential function, which is the distance for the limiting equation, for the limiting dynamical system, the distance from the fixed point. This weighted distance from the fixed point converges exponentially to 0. So essentially what it is saying is, if the limiting dynamics starts from a neighborhood, as a good neighborhood of the fixed point, then it converges to the fixed point. But how do, while establishing the limit interchange, how do we ensure that the limit of the sequence of steady states actually belong to that good class? We have no way to ensure that, but to showing that the sequence of steady state is actually tight in the corresponding topology. So if someone can improve this global stability statement by showing more stronger notions of convergence, then one can relax the tightness criteria, the topology in the tightness criteria. Okay. All right. So in summary, so we need this criteria for the process level convergence and this criteria on the graph sequence for the limit for the steady state tightness. So if both of these conditions hold, then limit interchange will hold. Now at this point, it feels very abstract, or two very abstract conditions. If they are satisfied, then limit interchange holds. What are the graphs that actually do satisfy these conditions? Going back to Shiva's question. So actually for that, we look at random graphs, and we ask that what is the minimum growth rate of the degree of servers that can ensure all these conditions on all these criteria. And first we consider random regular case where each degree is strictly bounded. So there's a strict constraint on the server degrees. And we say that we prove that if the growth rate of Dn is mn times log n over n, and if it is going to infinity, then both conditions are satisfied. Observe that if it is fully flexible system, like complete bipartite, then the degree of each server is mn. But now we are reducing it by almost a factor of n over log n. So it's sparsifying the system by a lot, almost by up to log n over n. Okay. And we also looked at average degree, like erosionary type constants as well. There, if the connectivity of the pairs of servers and task type, if they satisfy certain growth condition, and there also a lot of, one can just observe that it's almost reduced to log n over n, but it also depends on the how mn is growing relative to n and so on. So if it satisfies certain growth rate, then sparse systems can also satisfy these two conditions. And we extend it to inhomogeneous case as well. I don't want you to just read this, the exact criteria. It's essentially saying some task types can be more important. So they may have more routing choices, and some may have little bit routing choices. So we are able to handle that case as well. So with that, with the presence of that inhomogeneity, we are able to characterize the limit and all the limit interchange and so on. Summary, we analyzed the JSQD scheme for sparse compatibility graph structures. We extended the validity of in-field approximation for large class of sparse networks, and we established that the much sparser topologies or compatibility structures can enjoy the benefits of fully flexible systems, provided they are suitably randoms. So this field is only starting. Not much is known in almost anything. So there are a lot of open problems that we can solve in this community. For example, finite end bounds, rates of convergence, graph-dependent routing policies, heterogeneous server speeds, dynamically evolving or changing graphs, and so on, and many more. I just listed a few. And with that, I'd like to thank you all for listening, and we're happy to take questions.
Thank you very much. Thank you. And shall we move on to some questions, perhaps? Does anybody have any questions?
I have a minor comment. I'm Sergey, who's Just could you show me the list of references, please, again?
List of papers, you mean?
In the middle, when you made this historical reference, and I found my name there. And yes. So I'm just, I was puzzled actually, because this paper by Foss and Chernova, it deals with something very different. It's about optimality of first come first served discipline in multi-server queues. And essentially, I think you mixed up this paper with another one. My paper is not Chernova from 1998, and I will put it into I put just in the chat, and it's correct reference to you just to make it clear. Actually, it's different one. You see it, yeah?
Thanks a lot.
This is different. It's confusing to me. I was puzzled, to be honest. Okay.
Sorry about that. Thanks for the reference.
I think you meant exactly this paper. I think, yeah.
Thanks a lot.
What do you think the rates of convergence, what the rates of convergence are, if you don't mind? Sorry, my son walked in just as we were finishing up. Because I thought, sometimes you had this kind of Markov inequality. It's like m over n, and then other places you had a 1 over n. So I'm just wondering what you think are the kind of dominating, or is it 1 over d, where d was the degree earlier on? What are the things that determine how close things are to meet field limit?
So are you asking about rates of convergence?
Yeah, what are the rates of convergence? Does it depend on mn, n, dn, or just, any thoughts on that?
Yes, I mean, we do not have any sort of like explicit rates of convergence results because it depends on both the number of servers, number of task types, and a lot of other factors. But for the transient limit, as I said, that if the proportional sparsity condition is satisfied by like approximately, like there is some epsilon wiggle room and it's not satisfied for all epsilon, but epsilon larger than something, then we can sort of make a statement that the trajectory of the mean field limit differs from the trajectory of the limits of this system. They must be at most this with high probability. This type of statement we can make, but explicit rates of convergence we do not have.
Yeah, okay, that's fine. And the other thing, maybe you said it during the talk, and but this Lipschitz condition, does that hold for the kind of idle queue policies as well? You had this Lipschitz. In addition, are there ways you could like randomly choose amongst a set of queues, and then if there's an idle one there, send it there, or something like this? Because
this condition, you mean?
Yeah. How broad is it? I guess
no.
Really kind of more focused towards where you're going to have some independence between the queues, if you see what I mean.
Yes, like the join idle queue, for example, I guess which will not satisfy this type of conditions. This condition, for example, if you have no idle queue, then PI will be at random. So it's like it depends on the entire empirical queue length and quite smoothly. But then suddenly, if there is one idle queue, then the entire mass gets concentrated to that idle queue. So it doesn't sort of depend smoothly on my neighborhood or in my the queue length of empirical queue length distribution. So there's
sometimes wondered about like probabilistic things where you just sort of keep selecting queues until you find an idle one, or you have some randomized policy like that. I guess if you went for every you might end up asking a small number of times on average, and that anyway, it's just a thought.
That's a good point. Like if you for example have a threshold on that, like if you are going to sample at most this number of times, so that this number is a fixed number, then probably that can be encoded in this form. But if it is until you find an idle server or something like that, that becomes a random, and then I guess it may fall outside this class.
Yeah. Okay, cheers, thanks.
Thank you. Do we have any other questions? That's okay, so I'm going to stop the recording here. And feel free to stay and chat a little bit more as you wish. I'm gonna stop the streaming as well.
Ankur, just sort of maybe an open-ended question. Given that